So now we move on to our next set of functional groups. Our next set of functional groups are those where we're going to have carbon single bonded to an element that's not carbon. And so we're going to start with alkyl halides. So an alkyl halide is just a hydrocarbon bonded to a halogen. And in many cases, we just use the letter X to abbreviate any generic halogen. So we're talking about fluorine, bromine, chlorine, or iodine here. So alkyl halides, as we'll see later on in the course, are very, very useful in organic reactions. And they undergo a lot of organic reactions. In terms of interesting molecules, definitely not as many interesting uses, but we can see a few examples here. We have halon, which is used for fire suppression. We have halothane, which is used as an anesthetic. One of the more common organic ones that we use in the lab is chloroform, CHCl3. And then we have this other molecule, which you can see, the red algae. It's what produces their odor. It's what they use for defense. But that molecule, we can see, it's an alkyl halide because of these two halogens, the bromine and the chlorine. But it also has an alkene and an alkyne. So our next class of molecules, our next functional group, are alcohols. Alcohols are carbons bonded to an OH group. And we can divide alcohols up into primary, secondary, and tertiary. Now the definitions here are very, very similar to the ones that we saw for primary, secondary, and tertiary carbons. In a primary alcohol, the OH is attached to a primary carbon. In secondary alcohol, the OH is attached to a secondary carbon. And in a tertiary alcohol, the OH is attached to a tertiary carbon. And there is, of course, no such thing as a quaternary alcohol because that would require the carbon having more than 4 bonds. So we can see some examples of alcohols here. So on the left we have probably our most well-known or our most common alcohol. That's ethanol. That's the kind that is in alcoholic beverages. Isopropanol is rubbing alcohol. And this molecule, which you can see has an aromatic ring with an alcohol, is acetaminophen, or the active ingredient in Tylenol. Now, similar to alcohols are ethers. The difference between an alcohol and an ether is that where alcohols are an oxygen that's bonded to one carbon, an ether is an oxygen that's bonded to 2 carbons. Now, one of the interesting things with ethers is there's one ether that is much, much more common than all the others. And that's the one we have on the right here, labeled diethyl ether. In fact, diethyl ether is so common as an ether that it's often just referred to as ether. So if you're ever reading an experiment or an experimental procedure where the procedure calls for adding 20 milliliters of ether, that's always referring to diethyl ether. It is one of the most common lab solvents that we use. But there's also some other interesting stories we can tell about ether. Some of you may not know this, but the types of pipettes that you used in Gen Chem, the ones that measure 25 milliliters or 10 milliliters, those large pipettes, when you use them, you probably had large bulbs that you put on the top in order to pull the liquid up into the pipette. Well, years ago, those bulbs didn't exist. And you know how people used to use those pipettes? They used to treat them like a straw. And, not a very good idea. Something we don't do anymore. But it was especially a bad idea with ether. Why is that? Well, this might help us to see. So you can see here what's happening. That would be diethyl ether that they used to use in hospitals. And as he opened it up and inhaled too much of it, yes, ether can be used to knock you out completely. So people who I've talked to who are old enough to have used pipettes in that way said that was the one problem doing it that way, was it wasn't too bad unless you were having to work with ether, and then you had to make sure that you didn't get too lightheaded during the process. We can also see another interesting example of ethers in the middle. Again, we can point out multiple functional groups that we've seen, such as the aromatic ring, the alcohol, but the ether is right up here where we have carbon, oxygen, and carbon. Now you might notice that just like some of the alkenes we talked about, this molecule has a lot of pi bonds that are conjugated to each other. And so that makes it very, very colorful. And you can see what color it is just based on the name, red number 40. What is that compound used as? Well, you can see the example down here on this ingredient list. And right down here. Right down here you see red 40. It is used as a red food dye. All right, we have two other functional groups that go in this sort of general category. We have amines, which are molecules that contain carbon-nitrogen single bonds. We have primary, secondary, and tertiary amines as well. But here the definition is different from what we saw for alcohols. So a primary amine is when we have a nitrogen that's bonded to exactly one carbon. In a secondary amine, the nitrogen is bonded to two carbons. And again, we designate one with R prime to show that yes, they can be the same or they can be different. And finally, we can have a tertiary amine, which is a nitrogen that's bonded to three carbons. And here are some examples. So we have a tertiary amine here in nicotine. Dopamine has a primary amine, as does putrescine. So Amines, especially primary amines, don't always have the best smell. And you can see that from putrescine, which is responsible for the odor of decaying meat. And then our fourth example is alanine. Alanine is another one of the 20 amino acids. In fact, if you've ever wondered why they're called amino acids, no, it's not because they're mean. But the amino part of the name amino acid comes from the fact that there's an amine functional group within the molecule. Now, while amines are definitely not the most pleasant smelling compound, they're extremely pleasant smelling compared to thiols. Thiols are similar to alcohols, except that instead of an OH group, they have an SH group. Now, how bad do these smell? Well, back when I was a starting grad student, right around the year 2000, there was another grad student who was using this compound, benzene thiol. To say that benzene thiol smells bad would be an understatement. Now, if you use benzene thiol carefully and you know how to use it, it's entirely possible that you could use it and someone who's 2 feet away from you would have no idea that you're using it. But the thing that happens, especially in chemistry labs, is when we have to inject liquids into reactions, we generally use syringes. And that's because you don't want to open your reaction up to the air. Many reactions, if you open them up to the air, that can ruin the entire reaction. And so if you do that, instead you inject the reagent with a syringe. Now, in order to do that, uh, uh, the syringes and needles that we use in an organic lab are pretty long, sometimes as long as about 6 inches. And even after you inject what's in there into a reaction, there can be a couple hundred microliters, couple tenths of a milliliter left in that syringe. And so we often have, if we're working with thiols, we have to rinse the syringes with bleach and acetone and some sort of hydrocarbon. The person hadn't learned that yet, and instead of doing that, they actually rinsed the syringe with, or just rinsed it out in the sink. And at that point, those couple hundred microliters were enough to make us evacuate the lab for about 45 minutes. So here's some other examples of thiols. So thiols can include some of the molecules we have here in this, such as cysteine, which is another amino acid. The molecule on the right, methane thiol, not that useful of a compound other than for its bad smell. If you've ever smelled a natural gas leak, natural gas doesn't really have much of an odor, so they put a very, very small amount of methane thiol into it to use that as an indicator. And finally, you can see the thiol in the middle is the thiol that's responsible for a skunk's odor.